The next video lesson is on our notepad page, page 11. If you have that open, you'll see the title called Chemical Periodicity, where the first section will talk about classification of the elements. We definitely want to have our test-taking tool page out, the electron configuration pyramid, but probably more importantly, we'll have out our periodic table block where we have our S, P, D, F sublevels all written in for us. I did not hand you this over this before you left for summer, but it is a link here on our Moodle site that says test-taking tool page, please print me. So let's just be sure that you have access to one of these test-taking tool pages either by printing or for the first time or just pulling it out because you've already been looking at it. And what it does really is capture for us the last set of lessons. We're going to be introducing some periodic trends, atomic radius, ionization energy, and electronegativity. And we see that our test-taking tool page has those highlighted for us. We need to go through and kind of define what each of those means and talk about those trends on the periodic table. But our next section actually deals with really just another round of practice writing electron configurations, really in terms of periodic trends. What are some things that we notice, for instance, about the electron configurations of all of those atoms that lie in the first family, hydrogen's family? What is a trend in the way that they arrange their electrons? What is a trend in the way that the beryllium family arranges their electrons? We'll talk about the S block, the two tall columns known as the alkali and the alkaline earth metals. We hop over to the next tall area on our periodic table. Boron's family lying in the P1 column, carbon's family lying in a P2 column, P3 for nitrogen's family, oxygen's family lies in P4, fluorine's family entirely with P5s, and the noble gases, minus the helium, which only has 2 electrons, which would be an S squared, but neon all down will end with the P6. This area of the periodic table is known as the P block. There are 6 columns in the P block. We notice that interior, where the transition metals are, we know to call that the D block. There are 10 columns in the D block, indicating the 10 electrons that the D block can hold. And down below in the rare earth element, the lanthanide and actinide series, this is known as the F block. And the F block, of course, would represent the 14 columns, 14 electrons in the F sublevel. So a good majority of our time really is just taking electron configuration writing and showing trends in terms of families. Classification of the elements. Let's go ahead and begin filling in some notes. It says when we begin thinking about the periodic table in terms of trends, one of the first trends we can't help but notice is the way that the electrons arrange themselves according to the column that the element lives in. The columns, of course, we know as groups. All elements in the same column have the same number of valence electrons. So out of all the subatomic particles, the protons, the neutrons, the electrons, it's the electron that plays the most significant role in determining the properties of an element. It's the electron that gives an element its chemical properties. The arrangement of these elements on our periodic table depends upon these properties. So in our note pack, we have just taken the time to fill in our blank. Of the 3 major subatomic particles, the electrons play the most significant role in the field of chemistry. The arrangement of these elements on the periodic table depend upon those properties. Elements are not just randomly dispersed on the periodic table. There's very specific reasons they live where they live on that chart. And what we're trying to do is make some connections. Why do the elements in the first column appear where they are? Well, the answer lies in their electron arrangement. The number of electrons, especially in the outermost energy level, are what most interests a chemist. It will determine the reactivity, the bonding, the chemical and physical properties of an element. Elements can be classified into 4 different categories. And what we'll do then is just kind of talk about one category at a time and just show the periodic trend based on their electron arrangements. The first of the 4 categories are known as the noble gases. Let's jot down in our notepad, what are the noble gases? Well, those are the elements in which the outermost S and P sublevels are filled. The element that fills the S and P sublevels are called the noble gases. They comprise of helium, neon, argon, krypton, xenon, radon. Recall that every element envies the noble gases with that most stable configuration, that filled outer shell. Every element will form a compound, a bond, in order to achieve that noble gas arrangement. Noble gases are those elements that fill their S and P sublevels. Now let's show that trend in our notepad by writing for each of the noble gases. The noble gases have their S and P sublevels filled. Let's show that, and again, it's just a practice. What our goal is to take a look at how to move from the electron configuration pyramid in which we follow these diagonal lines, and to show then instead how to use our periodic table to figure out the noble gas arrangements. So for instance, helium, who's number 2, we have to write for 2 electrons. Helium lives in the first period, first energy level, in the S2 column. Its noble gas arrangement has the S sublevel filled. First principal energy level in the S sublevel are both electrons. Now notice it's only asking for electron configurations, not for the orbital diagrams, not the little circles with arrows. Let's keep the trend going. Here's neon, number 10. Neon lives in the second period in the P6 column. Read this periodic table as you would a book from the left to the right. Hydrogen, helium fills that first energy level, 1s2. We reach the end of the row, go down a row. We hit the second energy level, pass through the S block, 2s2, 2p6. We've just written for 10 electrons of neon. 1s2, 2s2, 2p6. The S and the P sublevels are filled for the noble gases. Keep going for argon. Argon lives at the end of the row in the third period. The last thing we'll write is 3p6. Argon has 18 electrons. On our periodic table, it's number 18. 1s2, 2s2, 2p6, 3s2, 3p6. Filling the third energy level. Follow one more for krypton, number 36. Krypton lives at the end of the fourth period. End of the fourth period, the last thing we'll write is 4p6. Read the periodic table as you would a book from left to right. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now notice the D sublevel gets hit in the fourth period, but the D level is always 1 behind the period number. So after I pass through 4s2, I hit 3d10, 4p6. And there we've reached krypton. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. The outermost energy level is n equal 4. The S and P sublevels are filled. A periodic trend for the noble gases, the S and P sublevels are filled. That condition always is true as the periodic trend in terms of the electron configuration for noble gases. A second category of elements are called the representative elements. Those are the elements, of course, in the tall columns. Let me kind of show you on our chart. Representative elements lie in the S block, and these representative elements lie in the P block. We called those the group A elements. With these elements, the outermost S and P sublevel is only partially filled. And we have some examples to write for. If noble gases have completely filled, these are only partially filled. That's what makes them reactive. That's what makes them be able to form bonds to make compounds. When we write for lithium, sodium, and potassium, here's a trend: lithium, sodium, potassium. Lithium, sodium, potassium all lie in the S1 column. Lithium we'll write until we go 2S1. Sodium, 3S1. Potassium, 4S1. The period indicates the level, the quantum level, and the column is telling me to fill it until we reach the S1. Now, we can do this shorthand just to review what we call the kernel structure. For instance, lithium. What's the last noble gas we pass through before we reach lithium? Well, that's helium. Doesn't save us a ton of time, but at least it could practice. In terms of writing for lithium, let's write helium in a bracket, 2S1. That denotes the 3 electrons for the element lithium. Sodium, who's number 11. Who's the last noble gas we pass through before we hit sodium? Well, that's neon, the end of the second energy level. So neon goes into a bracket, 3S1. There's the 11 electrons for sodium. And potassium. The last noble gas we pass through for potassium is argon, the end of row 3. The end of row 3 allows us to write 18 electrons, 4S1. Notice the periodic trend. Lithium, sodium, potassium live in group 1A. They have 1 valence electron. All have 1 valence electron. 1 electron in their outermost energy level. And that's why they live where they live. A periodic trend. One trend that we're discovering is that all elements that lie in the same column have the same number of electrons in their outermost energy level. The column determines how many valence electrons. The period number, the rows going across, tell me how big the energy levels are, how many rings from the planetary model. Let's try another trend, carbon, silicon, germanium. Carbon, silicon, germanium. They all lie in the P2 column. Carbon, who's number 6. We have 6 electrons to write for. Carbon is going to end with the 2p2. The last noble gas we pass through is helium. We have to pass through the 2s before we land at the 2p. Helium, or you could write 1s2. Helium in a bracket doesn't save you a ton of time. After you hit the end of row 1, you must pass through the 2s2 and end at 2p2. You must write the number of electrons that equals 6, carbon's atomic number. Helium has 2 electrons. 2 plus 2 plus 2 is 6. Let's try silicon next. Silicon is in the 3rd period, P2 column. The last thing we'll write is P2, 3P2. Who's the last noble gas you pass through before silicon? Well, that's neon, the end of row 2. So if we place neon in a bracket, silicon, by the way, if we haven't written that yet, is number 14. When I write neon, neon is number 10 on our periodic table. That saved me from writing 10 electrons. After neon, I go down to the next row. I must pass through the 3s block before I hit 3p, 3s2, 3p2. Notice a trend. We have now 10 from neon, 11, 12, 13, 14 electrons written for silicon. Let's try one more, germanium. Germanium is number 32. Who's the last noble gas you pass through before germanium? Well, at the end of row 3 is argon. Argon is going to save me from writing 18 electrons, so argon goes into the bracket. The end of row 3 is argon, so I go down to row 4. That's the 4s squared block. What do we hit after 4s squared? We hit the 3d10 sublevel. Then I hit 4p2. So after argon, 4s2, 3d10, 4p2. Read it like a book. 4s2, 3d10, 4p2. Argon is number 18. 2 plus 10 plus 2 more is 14. That indeed adds to the 32 we needed to write for germanium. What's the trend? Silicon, germanium, and carbon, those 3 elements, lie in the family known as group 4A. They all have 4 valence electrons, 4 electrons in their outermost energy level. There, I got it spelled. All have 4 valence electrons. Representative elements have partially filled S and P sublevels. The number of valence electrons matches their group number. The highest energy level occupied matches their period number. One category of elements based on their arrangement of electrons are called the noble gases. A second arrangement of electrons partially fills the S and P sublevels. Those are what we called the group A elements, the representative elements. Group A's, the tall columns on our periodic table. There's a third family of elements based on the way that they arrange their electrons, and those are called the transition metals. The transition metals are the shorties in the middle. These are the metallic elements in which the outermost S sublevel and nearby D sublevel contain electrons. I'll put that back up in a moment. When we pass through the S sublevel, we must pass through the S sublevel before we hit a D. So my definition is including you must pass through the S and then hit the nearby D sublevel. The transition elements always contain partially filled D sublevels, the D block in the center. You got to pass through an S, then you hit the D. Remember, the S block matches the period number, but when I go to start filling in the D level is always one behind the period. Let me repeat the definition for us. Transition metals are metallic elements in which the outermost S sublevel and nearby D sublevel contain electrons. Transition elements, those shorties in the middle, those transition metals, are what we call the D block. Now let's show the trend in terms of zinc and zirconium. Oops, and I didn't put on the PowerPoint slide. Manganese. We can start with manganese. Mn. Mn is number 25. Let's find it on our test-taking tool page. Here's manganese. Manganese is in the 4th period. Knowing that it's in the 4th period allows me to predict I have to pass through the 4s2 sublevel, then start filling in the 3d sublevel. Manganese is 5 over in the D block. The last thing we'll write is 3d5, and we'll have written for the manganese. Let's do it shorthand just to practice that kernel method. The last noble gas we pass through before hitting manganese is argon. Argon is at the end of row 3. So in a bracket, I'll place argon. We're at the end of row 3, so we go down to the next row. That's the 4th period. What do we go past through here? We're going to pass through the 4s sublevel. After we've gone through 4s2, we now hit 3d. 3d5 brings me to the manganese. 3d5. Transition metals, let's just remind ourselves that definition, have outermost s sublevels and the nearby d sublevels containing electrons. Transition elements, you'll put a noble gas in a bracket for the last one you pass through. You'll fill an s sublevel and start filling electrons in the nearby d. The d's are always one behind the period number. Let's write for zinc. Zinc has atomic number 30. The last noble gas we pass through, it's the same. Manganese, a little further down, is zinc. It has the last noble gas again to be argon. So argon in a bracket. 4s2, 3d10. Argon is number 8. Argon is number 18. 19, 20. 10 more gets us to 30 electrons. Zinc is in the 4th period. After I complete argon, pass through it, I hit the 4th energy level. I pass through 4s2. The D is always one behind the period number. I complete 3d10, and I'm at zinc, 30 electrons. Zirconium. ZR, zirconium, is number 40. Zirconium is in the 5th period. We pass through the 5th energy level, 5s2, before we hit zirconium, who's in the 4d sublevel. Who's the last noble gas? Who's the end of the row in row 4? That's krypton. So krypton in a bracket. That takes me to the end of row 4, krypton. I come down a row and hit row 5. That's the 5s2 sublevel and 4d2. So I still have to write 5s2, 4d2, and we've written for zirconium. We've talked about the noble gases having their filled S and P sublevels, the first category. We've talked about the representative elements that have partially filled S and P sublevels. The D block, those are called the transition metals with the S sublevels and nearby D sublevels representing their periodic trend. Notice what we've written. We're thinking periodic trends. Transition elements, those shorties in the middle, the group B's, have S. I can even put 2 because we'll always pass through the S block before we get the D. And partially filled, well, I don't mean that because zinc was filled, and D sublevels. I say that zinc had a filled D sublevel. So the trend is that we're noticing we'll have an S and then move into the D. This is called the D block on our periodic table. That leaves us with one more category, the 4th category, the inner transition metals, which are located in the bottom 2 rows, those rare earth metals, or the lanthanide and actinide series. These are metallic elements in which the outermost S and nearby F sublevels generally contain electrons. The rare earth elements, the inner transition elements, the bottom two rows, I'm trying to say that multiple ways. The inner transition metals, or the bottom two rows, have their S and nearby F sublevels containing electrons. That's this guy down here. The inner transition elements, you'll hit an F block. And these get quite, down here you're always 2 behind the period when you start filling the F block. So that just takes us with practice, recognizing periodic trends with this particular test-taking tool page. This appears in your notepad, but maybe what's handier is that the test-taking tool page I actually put information on, the numbering and so forth with that. I want us to move away, best we can, and it just comes with practice, move away from needing this pyramid and start thinking of the periodic table in terms of trends. Elements that lie in the same column have the same number of valence electrons, the same number of electrons in their outermost energy level. Elements in the same row contain the same number of energy levels, n, the principal quantum number n. At this time, let's practice using our periodic table. Practice. So what I'm asking you to do on the top of the next page, pause the video. Please pause. You fill out the video, or you fill out the notepad and start up again when you're ready to check your work. Don't cheat yourself. Practice first as an individual, then come back to check. Welcome back. Let's check our work. We're going to check for the electron configurations of these elements. Nitrogen. Nitrogen is in the second period. The last thing we wrote was 2p3. If you wrote 1s2, 2s2, 2p3, you have written for all 7 electrons of nitrogen. How'd you do for nickel? Nickel is in the 4th period, so I'm going to pass through 4s2, and it's going to start filling its nearby D sublevel, 3d, and the last thing you wrote was 8, 3d8. The last noble gas you passed through was argon. You then went 4s2, 3d8. Argon, 4s2, 3d8. Vanadium, 3d3 was the last thing you wrote. The last noble gas passed through was argon. 4s2, 3d3 brings you to vanadium. Nickel, number 28. Vanadium, number 23. Good things to add on. What are all the symbols for the elements that have the following outer configurations? Who are the elements that would end with S2? Beryllium would, so would magnesium, so would calcium, strontium, barium, and radium. All of those elements. Beryllium would be 2s2, magnesium 3s2, calcium 4s2, strontium 5s2, barium 6s2, radium would be 7s2. All of those elements would have an arrangement that ended with an S2 configuration. What about the S2P5? Passing through the S and getting to the P's. Filling the S, arriving at P5, here's the column. Fluorine's family would all end with S2P5s as their electron arrangement in the outermost energy level. Fluorine would end with 2p5, chlorine with 3p5, bromine 4p5, iodine 5p5, and astatine 6p5. So, fluorine's family, fluorine, chlorine, bromine, iodine, and astatine all end with S2, P5 configurations. And the letter C, passing through the S sublevel, ending with D2, you get TI, ZR, HF, RF. There's 4 elements that meet that criteria. Passing through the S block and ending in the D2 column, titanium, zirconium, hafnium, and rutherfordium. 4 elements meet that criteria. You should pause your video here. This completes this video lesson, and I want you to tackle appropriate recommended assignment questions to check for your understanding, and also take a look at the multiple choice piece to this and tackle what now feels comfortable. Come back to the video lessons, come back to your notepad when you've mastered this skill.